Good afternoon, everyone. Thank you for your attending. It is my great pleasure to present another talk on the on our recent work on the ISS internal multiple elimination algorithm. First, let me explain the abbreviation we used in this presentation. The ISS-IMA represents the inverse scattering series internal multiple attenuation algorithm developed by Arthur Weglein al. And this internal multiple attenuation algorithm can predict the internal multiples of all orders with accurate time and approximate amplitude without any subsurface information. ISS-IME represents the inverse scattering series internal multiple elimination algorithm developed by Zou and Weglein, Zou et al. As mentioned by my colleague earlier this morning and prior to this presentation, currently this elimination algorithm will predict the internal multiple of all first orders and only with p history, with both accurate time and accurate amplitude without any subsurface information. So in the last presentation, my colleague Yanglei Zou presented a 2D test of the ISS-IME based on a 2D acoustic model we shown here. So we designed this 2D model to mimic a salt play, and we designed this model such that we have a base salt primary which is destructively interfere with an internal multiple such that the base salt primary is invisible in the data. The results of the ISS-IME after removing the internal multiple is very impressive and encouraging. We can see this base salt primary is recovered, whereas the currently most capable methods, the ISS-IMA plus adaptive, failed to recover this primary when removing the internal multiples. So we have this very encouraging recovered primary by this ISS-IME method. The question is how well this primary is recovered. In other words, is the interfering internal multiples is removed by the ISS-IME without damaging the primary? Well, to answer that question, we would like to take this recovered primary and compare it with the recovered primary with the actual primary in both time and amplitude. However, the challenge is how to use with theoretical modeling methods which honors both the time and amplitude of the wave to generate the primary only events in a 2D case. For example, for the wave theoretically data modeling methods, finite difference, for example, cannot generate primary only events in a multidimensional case. So to allow such a comparison, we proposed a complementary test using this 1D model, which is very close to this 2D acoustic model, where we, just like the 2D acoustic model, we designed this 1D acoustic model to allow an internal multiple and a primary destructively interfere. So, and also in this 1D case, we can use like with finite reflectivity methods to generate the primary only events to compare the recovered primary with our actual primary to see if this the ISS-IME can recover the primaries without damage it. So the focus of this presentation is we use this 1D acoustic model to see if the interfering primary can be recovered without damage. So in specific, in this 1D example comparison, we will compare the recovered primary by the ISS-IME and the recovered primary by the ISS-IMA combined with the adaptive, comparing these two results with the actual primary and in both time and amplitude. So based on this 1D acoustic model we shown here, we use the reflectivity method to generate the data on the right. We have the first primary corresponding to the first reflector. We have the second primary corresponding to the second reflector. We have the third primary corresponding to the third reflector. And we have the internal multiple 212 generated by the second reflector, first reflector, second reflector. where we can see that the third primary and the internal multiple 212 destructively interfere at around the offset 1,000 meters. So here we show the prediction results of the first order internal multiple coming from the ISS-MA on the left and the ISS-ME on the right. We can see the time prediction of the internal multiples, they are the same, which is agree with the actual internal multiple in the data. However, we can see they have different amplitude prediction from these two plots, as we expected, because the internal multiple prediction from the attenuation algorithm has an approximate amplitude compared with the actual internal multiples in the data, whereas the prediction results from the elimination algorithm has the exact amplitude compared to the actual internal multiple in the data. So next, I will show three sets of comparison. In the first set, I will take the results from the ISS-MA and directly subtracting these prediction results from the actual data and compare these results with the actual primary. And in the second set, I will take the results from the ISS-MA and combine this prediction with adaptive and compare these results with the actual primary. And in the third test, in the third comparison, I will take the results from the ISS-ME and subtract the internal multiple prediction from this ISS-ME from the data and compare these results to the actual primary. So first, let's look at the first comparison. So before I show you the comparison, I would like to remind you that this internal multiple prediction result from the ISS-MA provides the internal multiple prediction with accurate time and approximate amplitude. So if we directly subtract this approximate internal multiple prediction from the data, we would expect some internal multiple residuals left. So here we show the comparison between this actual primary and the results from the ISS-MA. And for either comparison, for either reference, we also plot the actual primary and internal multiples on the left. And with this internal multiple being partially removed by this approximate internal multiple prediction from this ISS-MA, we can see two observations in the results from the ISS-MA. First, with this internal multiple being partially removed, we can see at the places where the primary and internal multiple destructively interfere, the primaries are partially recovered because the internal multiples are being partially removed by the result from the ISS-MA. And at the places where primary and internal multiple they do not overlap or do not interfere, we can clearly see the residuals left as we expected, because this is an approximate prediction results, which we can see the residuals left. So now let's look at the results from the ISS-MA combined with the adaptive and compare these results with the actual primary. So here we show the comparison between the primary and the results from the ISS-MA combined with the adaptive. Also, for either reference, we provide the actual primary and the internal multiple in the data on the left. So now when we add the results from the ISS-MA without the adaptive and comparing these results, we find first where the adaptive helped to remove the internal multiple residual left by this ISS-MA results, where the internal multiple does not interfere with the primary. We can see the results from the ISS-MA alone will have some residuals, whereas the adaptive is very effective and helpful to remove this residual at the place where they do not interfere. However, the adaptive can actually harm the primary, which partially recovered by this attenuation algorithm. Now let's look at the results from this ISS-ME by directly subtracting its result from the data. So here, the two figures on the right show the actual primary and the results from the ISSME by direct subtraction. And again, the figure on the left shows the actual primary and internal multiple in the data for easy reference. And now we add on the results with and without, the results from the ISSME with and without adaptive. And comparing these results, we can see, so with this amplitude improved prediction from the ISSME, the amplitude improved in the sense that the internal multiple prediction results from the ISSME can predict the exactly amplitude of the internal multiple, whereas the internal multiple prediction from the ISSME can provide a approximate amplitude prediction from the ISSME. So with this amplitude improved prediction of the internal multiple, without using any adaptive procedure, the results from the ISSME can remove the residuals left by this ISSME. As we can see, these residuals left by this ISSME can be directly removed without any adaptive procedure in the result from the ISSME, because this improved amplitude prediction from this ISSME. And because at the same time, because we don't use any adaptive procedure in the result of ISSME, we won't have hurt this recovered primary in this interfering zone where primary and internal multiple destructively interfere. And not only that, because this amplitude improved the prediction of the internal multiples, the primaries recovered by this ISSME will be better recovered by this partially recovered primary by this ISSME result. The ISSME algorithm can remove the interfering internal multiples and never damage the primaries. So separate from the 1D acoustic model, previously 1D elastic model is revisited here. And this 1D elastic model was done by my colleague Yanglei when he interned at Schlumberger. Back then, he compared the results from the ISSME and the results from the ISSME and compare this result to the actual primary. So what's new here is we would like to know what would happen if we use the ISSME plus adaptive. So what we add here is we take the results from the ISSME plus adaptive and add to this comparison. So first, the data on the right shows the synthetic data used in this elastic example generated by this 1D elastic model. And the comparison focusing on this one part of this data highlighted by this red box. And on the next slide, I will only show the data in this red box. So here we show the data in the red box. And we focus on 3 events in this area where we use blue line represents the internal multiple and the red line represents the primary. These two plots are the same, except on the left we highlighted the events using the blue line and the red line. Notice that here the internal multiple are always p history. So first, let's compare the results from the ISSME by directly subtracting its result from the data with the actual primary. And again, for easy reference, we provide the data with and without events highlighting on the left. And when we compare the actual primary with the result from the ISSME, we can see first, at the places where the internal multiple and primary, they do not interfere, do not overlap, we can clearly see some residuals left because, again, this is internal multiple prediction with approximate amplitude, so this residual is expected. And also at the places where they do interfere, we can clearly observe the amplitude difference, which also indicates the internal multiple residuals over there. And now let's add on the results with from the ISSME with adaptive. First, we can see the residuals left by this ISSMA can be removed by the adaptive procedure. Now, very good, like shown here. And however, at the places where the primary and internal multiple partially overlap, we can see this distortion. And at the places where the primary and internal multiple completely overlap, we can see the ISSMA plus adaptive can remove the internal multiple, but at the expense of the primary. You can see the primaries, there are no primary left here. Now let's look at the results from the ISSME by subtracting the elimination results from the data. And this result from the ISSME is shown in the middle panel, the second row. So by comparing these results, and we can conclude the same conclusion we get from the 1D acoustic case is this ISSME results can nicely recover this primary when it's interfering with the internal multiple without damaging the primary. Again, the key here is the ISSME can remove the interfering internal multiple without damaging the primary. So now let's draw the summary. So in this presentation, we demonstrated that the ISSME can remove the interfering internal multiples without damaging the primary. And the work on the ISSME is part of a three-pronged strategy to directly respond to the challenge of the removing internal multiples that are interfering with the primary and without damaging it. So the first aspect is the prerequisites for onshore application. This presentation has been covered earlier this morning by my colleagues. And the previous presentation and this presentation covers the topic of the ISSME. And as mentioned in the earlier presentation, the future work of the ISSME includes they develop a more complete ISS internal multiple elimination algorithm with the consideration of a high order internal multiple elimination, because as we mentioned, the currently elimination algorithm is aimed at to remove the first order internal multiples. And also future work includes the consideration of the inelastic and unelastic effects. Again, this current internal multiple elimination algorithm is after the internal multiple with P or with only P history. We will, in the future, we will develop a more complete elimination algorithm with the consideration of these elastic and unelastic effects. And the last aspect of this three-pronged strategy is we will have a new adaptive criteria for the internal multiple. And I think in next presentation, Professor Weglein will give us a adaptive criteria for the free surface multiple, and we will look into this similar criteria that derived and aligned with the algorithm for the internal multiple. So, so the bottom line is this is the toolbox option. And for isolated primary and internal multiples, so what we previously delivered, the ISSMA plus the energy minimization adaptive subtraction is sufficient and enough to remove the internal multiple without damaging the primary. And when the primary and internal multiple interferes, the ISSMA plus adaptive can fail, because when they destructively interfere, the energy after the removal of internal multiple can actually increase instead of decrease. So the adaptive criteria fail. So, and what we provide here is a toolbox, tool in your option in your toolbox that can remove the interfering internal multiples without damaging the primary. So with that, I will thank our sponsors and thank you for your attention. I will welcome questions you have. Thank you very much.